I'm a CNRS researcher at LPG in Nantes in France. I've been there since 2015, and I arrived there after doing a couple of postdocs. So I did sort of forwards and backwards between France and the UK. So my PhD was at the Open University in Milton Keynes, which is north of London in the UK. Then I did a postdoc in Nantes at LPG. Then I came back and did another postdoc for 4 years in the same place, Open University. And then I was recruited in CNRS in 2015. And I'm a planetary geomorphologist. My PhD, I studied debris flows on Earth and Mars, so slope processes on Earth and Mars. And I've continued studying things that go downhill on planets, both Earth and Mars, since then. And I'm going to talk to you today about these different bodies in the solar system, and we're going to start close to the sun, and then we're going to go further away bit by bit. I'm going to skip this one, I'm going to skip this one. We know these quite well. I could talk about those for another hour. And then we're going to go to Mars, where I'm going to spend a bit more time. And then if we get time at the end, I might go a bit beyond Mars into the asteroid belt to the dwarf planet Ceres. So we'll see if we get time for that. So the picture you see here is obviously the distances are not right, but the scales should be. So you have the sizes of the different planets there. And so as I said, we're going to start at Mercury. Mercury is not a very hospitable planet. I'm hoping to show you during this hour and a bit basically the diversity of the terrestrial planets in our solar system, what that means for habitability, but also I'd like to share with you some of the surprises I've had in studying these bodies. And especially Mercury was a great surprise for me. I only started studying Mercury very recently, maybe in the last 5 years. And I thought Mercury was a dead, boring planet with just craters, which is kind of true, I suppose, in some ways, but also has some surprises, which I'll show you. So Mercury, closest planet to the Sun. Its diameter is about just under half of the Earth's. It has a lower gravity, therefore. It has a year that is 88 days, and 1 day is about 2 years long on Mercury, so a bit strange compared to what we have on Earth. It has no atmosphere. That makes for a fun time for a geomorphologist because there's all sorts of processes I'm not used to, like solar wind hitting the surface and things like that. Very intense surface radiation and cratering, very extreme surface temperatures, but it is one of the few bodies in the solar system to actually have an intrinsic magnetic field, which makes it exciting for physicists. So I'm excited too, but it makes it very exciting for physicists for exospheres. So Mercury, I'm just going to quickly bring up, this is the exploration of Mercury. It's actually quite a difficult planet to get to, and so until the MESSENGER mission, in fact, very recently we had actually only data from telescopic observations and flybys. And so we actually had a very limited data set, and the image I showed on the previous slide, that is actually one of the data sets we had from the Mariner 10 flyby, which seems quite good, but actually the resolution is not great. So essentially all the things I'm excited about you can't see on these photos. And so we had to wait till the MESSENGER probe to actually get some really decent images of the surface. And actually while MESSENGER was crashing, low altitude orbit, we actually got images at 4 meters per pixel of the surface of Mercury, which is quite outstanding for this planet. So yeah, as it says, 33 years of gap between MESSENGER and the Mariner missions. So actually a planet with not very much data. And I'll talk a little bit at the end in starting, approximately a year's time, we're going to get the first data from Bepi Colombo, a European mission to Mercury, which should hopefully provide some answers to some of the enigmas we've been finding on the surface using the MESSENGER data. So this gives you an idea here, 700 Kelvin, 450 Kelvin, of the surface temperature extremes on the planet. These move with time, obviously, as the day progresses. but you can see that Mercury undergoes extreme surface conditions. I wanted to talk very briefly about the unusual size of Mercury's iron core and the fact that actually the origin of this body is quite debated, because we don't really know why the iron core is so big with respect to the rest of the planet. Was it some strange impact? Was it vaporization by the solar wind because it's so close to the sun? Or some other exotic mechanism? There's lots of debates in the literature about that. So actually, finding out more about Mercury can tell us about the formation of planets in general. So it is actually a very interesting body to go to, especially if we want to study exoplanets and understand how planetary systems form in general. So one of the geomorphologically obvious things on the surface, and was seen since Mariner data, is the fact that this whole body has been contracting and losing diameter. And so what that shows up as on the surface is these sort of wrinkles. They are actually called wrinkle ridges. This is actually a lobate scarp, actually bending of the crust. And this is a map, so in red are mapped these kinds of structures. Here's scale bar 150 kilometers. So they're all over the surface. And Ben Mann, a student of mine, in the sort of the black dots and the orange dots are actually evidence that these faults have been moving recently. Recent is geologically speaking, so I'm talking the last billion years rather than the last 3. So actually the contraction on Mercury has been ongoing, and it leaves its trace on the surface. And so we can use image data to understand that Mercury has actually been shrinking. So this is kind of the state of knowledge that we had at the, let's say, at the beginning of the MESSENGER mission. One of the things that we found out, though, is that actually Mercury is one of the most volatile rich. So the potassium-thorium ratio can be used as a proxy for the amount of volatile elements in a body. And you can see that amongst the terrestrial planets, Mercury is not far from the same volatile content as Mars. So we should expect some surface expression of that. And we do find it. So one of the surprises with the arrival of MESSENGER was this evidence of explosive volcanism. And you can see this in the form of these irregular pits. And these irregular pits on their own wouldn't be very convincing evidence without these beautiful, what they call faculae, which are basically colored splotches, very technical term. On the surface, they have fewer craters, they're younger. And these are a ballistic ejecta, essentially. From the sputtering of the lava on the surface, you form this very low relief dome around these pits. And these orange faculae are actually geologically recent again, and I'm not talking yesterday, but billion-year timescale, very recent. And we find these all over the surface of Mercury, and I'll show you that in a second. And their morphology is kind of fun. They have lots of, their floors have lots of different ages. And we can tell that they've not just been active once, but active several times over the history of Mercury, and we find inactive ones as well. The other thing we find on the surface of Mercury, which is a surprise when MESSENGER arrived, was these things that we call hollows. Again, more irregular pits, but they have a strange irregular shape, bright halos around the outside, and they seem to be eating away at the surface. And these pits are thought to be caused by loss of a volatile substance in the near surface. So near surface being tens to hundreds of meters thick, they're flat floored, and they appear to be growing. We don't have any evidence they're growing, so hopefully when Bepi Colombo arrives, we'll get some new images of these, and maybe we'll see they're growing, and that'd be really cool. We're hoping to. They didn't see them over the course of the MESSENGER mission growing, but they seem to be expanding outwards. So again, a surprising new process that we haven't found on any other body happening on Mercury. And related to these hollows on Mercury, there's also slope lineae, which may be not so surprising in fresh craters. You just have a different color material going down slope. But on low slopes like this one here, you have to have something to make the flow go downhill. And so what we think is that the bright color is the same color as in the hollow, so it's a volatile species. It's something that's going from solid to not solid, gas possibly, and then escaping. Sublimation is not the right word because you don't know whether it's actually something that's going from solid to a gas. It's probably just something that's disintegrating. And so this is motivating flows that go down slope and maybe even forming these little aprons at the bottom of these little channels on here. So we can get channels and debris aprons on airless bodies without liquid flowing downhill, which is kind of fun. And we'll come back to that again later on when we come to talk about Mars, because this is something I'm quite interested in. So this is the map, just to show you that I'm not talking about like one image or two images. I'm not showing the best ones. These are actually things that are found all over the surface of Mercury. So in yellow are those hollows that I just showed you. So they're pretty much everywhere. And when you zoom in, you get those 4 meter per pixel images I was talking about. You zoom in on a spot without hollows, they'll be there. And they're just too small to see on the images that we have from Messenger. And the black dots are these volcanic vents, which are, again, everywhere. So these are really common processes. It's just with the old data, we couldn't see them. So the high resolution images we get, the more puzzles we get, but it becomes more fun. So the other fun thing about Mercury is that we've known for a while that we have ice in permanently shadowed craters. And so this was first detected by using the volume scattering signal that we can see from Earth, these bright deposits in the bottom of craters. And again, so this is a publication in 1992. And has been confirmed with Messenger by using several data sets, the laser altimeter. So basically, these permanently shadowed parts of the craters are bright. And these are the craters in the neutron data. So hydrogen is a good absorber of neutrons, so you get very low neutron count. And that corresponds to these areas which are permanently shadowed. So with the topographic data we have from the Messenger, we're able to predict where those shadows, permanent shadows, should be just by doing a simulation of where the sun should be in the sky. And so what you're seeing in this plot is the permanent shadows correspond to where, from Earth, we're seeing the radar bright materials using Earth data, using data from Earth observation, and also permanent shadows. And they coincide almost exactly. And as a very cool thing, the Messenger team were able to reprogram their camera to look into these shadows. So they basically said, okay, we're going to put the exposure, a long exposure on the camera, and we're going to look into these shadows. So they totally saturated everything in their image apart from inside the shadows. And what they saw, so these are these images, what they saw is there's a permanent shadow here, but then there's a bright line inside the permanent shadow. So I think you can probably see that. I think it might be dark enough in here. You can kind of see that here. So there's actually a bright line visible within the permanent shadow, which we think is water ice sequestered in these permanently shadowed areas. And we have Messenger was in a elliptical orbit, so it had very good observations of the northern hemisphere, but poor observations of the southern hemisphere, so we don't have the same for the southern hemisphere. But terrestrial-based observations show we have the same thing in the permanently shadowed regions in the southern hemisphere, maybe even more of these ice deposits actually in the southern hemisphere. And so that's kind of cool, and Bepi Colombo will be looking at those, and we'll actually find out if we see these similar bright deposits, thick deposits of water ice inside these craters in the South Pole as well. And if we do, then the sort of equivalent amount of water is the same as the Great Lakes in North America. So it's not a small amount of water. It's not just a little, frost. This is a considerable amount of water that's being stored and cold trapped in these craters at Mercury. And that was actually something that was predicted from observations from Earth. But without this additional data from Messenger, we wouldn't have been able to estimate this in detail. So looking forward to Bepi Colombo. Finally, it's in flight. Everything's working nominally. And it's a series of several spacecraft, and at the moment they're all stuck together, but they'll all separate when next year, I believe. And then because the camera is in, the high resolution camera is sandwiched between the two bits of the spacecraft, we won't actually get images until the separation occurs. So fingers crossed everything works, and the camera works as expected, and we can get some new images. And because Bepi Colombo will be in a circular orbit, not elliptical, we'll get good views of the southern hemisphere as well as the northern hemisphere. And so I'm really looking forward to those new observations and trying to puzzle out what is going on with these volatiles on Mercury. So, as I said, not an inhospitable environment, but surprising surface processes. And I think we're going to have more surprises when we have this high-resolution data from Bepi. So next, Venus, our sister in the solar system, the morning star or the evening star, very visible from Earth, and very similar in some respects to the Earth, very similar radius, very similar mass, density, gravity, distance to the Sun, but substantially different in many ways as well. So it's our sister, but how did Venus end up so different from us? Why aren't there these big blue things here? We have a different rotation period, retrograde actually, different year length, the obliquity is extremely different. The atmosphere, as you know, is extremely thick with 90 bars of pressure at the surface, a stable 460 Celsius, doesn't change very much, it's always 460 Celsius at the surface. Different albedo and no magnetic field. So a very, very different surface environment, which actually makes it really challenging to observe and inhospitable as well. Another inhospitable planet, which starts, we start to ask ourselves, well, why we're a planet so similar in initial mass and composition should be so different from our own. And so we've always known that Venus had a thick atmosphere from telescopic observations. We can actually see the atmosphere here against the background of the Sun. And this led people to say, okay, we've got underneath all these clouds of Venus, we have life and exotic things are going on, but that was kind of all crushed when we got more detailed observations of the surface and more deeper understanding of the atmosphere. Here you can see Venus as shown by different wavelengths of radiation, UV, visible, infrared. Basically, you're just getting lots of images of clouds at each of these, which is fascinating and great for atmospheric scientists. But if you want to study the surface geomorphology, it's kind of useless. The only thing you can study the surface and the shape of the surface with is radar. That's the only thing that's going to penetrate those clouds. And so, because of these difficulties of examining Venus, actually, there's been more missions to Venus than there have been to Mercury. We actually have, a bunch of spacecraft, but you notice here that each of these diamonds is a short-term mission. So very few that have actually stayed a long time. So Venus Express and Magellan and Pioneer here are all ones that have been in orbit, sustained presence around Venus. Notably, though, we do have landers who have gone to the surface, all from Soviets. And they've also given us really great information about the surface of Venus. So we rely on the old Magellan data for most of our current knowledge about Venus, and excitement's building because there's going to be 3 new missions, which I'll talk about in a minute, to Venus, all pretty much at the same time. So we're suddenly going to know a lot more about Venus, and maybe there'll be more surprises, but to be honest with you, it's quite surprising already. This is the surface of Venus, so we have a topography data from the radar, where the sort of red colors are high mountains, and the blue colors are plains. And all of these are basically the names of volcanoes. And if we look at if we look at the number of impact craters on Venus compared to, say, Mercury or the Moon or Mars, there's actually, not compared to Earth because there's hardly any, there's actually not very many craters, like 900, less than 1,000 impact craters on the surface of Venus. And they're quite well spread out. They're not like, there's not concentrations in a particular area, which shows that the surface is pretty much a uniform age, which is surprising. And that age is, if you do statistics, you can work out that age is about 500 to 750 million years, which is super young. So that means that something is going on at the surface of Venus to recycle the crust. On Earth, we have few impact craters on Earth because we have plate tectonics that recycles the crust. On Venus, do we have plate tectonics? That's a big question. We don't think so. But we have plate tectonic-like things, maybe. We do have a lot of volcanic landforms. And these are not volcanoes you might recognize from the Earth. Pancake domes, for example, we don't have such things. But there are things that do resemble things we have on the Earth, like lava flows of different viscosities here. These canali are so sinuous channels, so lava channels. Little volcanic domes, so we have those. But we also have, like I said, weird, strange things that we don't really have on Earth. So there's lots of volcanic landforms. And the volcanic surface is confirmed also by the landers that we have. So the Soviet program, I love these images because it's just so cool to have such a close picture of the surface of a planet you can't hardly see on. So this is what those landers look like, more or less, artist's impression. And they're sitting on the surface and taking pictures. And the rocks they have around them are basaltic rocks. And you can see this is very yellow because there's very little light that actually gets to the surface. And if you actually put these at the real luminosity, we wouldn't be able to, these images would be black to your eyes, basically. You just can't see anything. So I think these images are pretty incredible and show a variety of rock shapes and sizes, which is kind of intriguing. Sand as well. So a very familiar looking surface to a geologist, but still on a planet that seems to be quite strange. And again, as I said, we find things on Venus that we don't find on Earth. Coronae is one of them. Circular tectonic features, which have diameters of hundreds of kilometers. They have a range of different shapes from the radar data, but they're thought to be related maybe to some kind of possible subduction or start of subduction. And models have basically shown that the younger versions here, so these sort of might have these kind of lips of material that are going down, whereas the sort of ones with the strange textures in the middle might have more advanced subduction. So possibly these coronae are some kind of like surface recycling on Venus. Another kind of plate tectonics has been suggested with these tesserae, which are many, many cracks. And you see many terrains like this on Venus, these parallel, semi-parallel bunches of fractures. And so this is kind of thought to be jostling of plates on the surface. And this is over 1,000 kilometers wide, this field of view. And you can see that, this is a publication in 2021, Magellan data that was taken decades ago. So, we can still do some good stuff with old data, but it's just about time that we got back to Venus and started to look at the surface again. Now the question being, okay, so we have this young surface, so we should be able to see Venus should be active. There should be some evidence of something being renewed, the crust being renewed. And so people have been looking for this, and so this is from telescopic and orbital measurements, 40 years of sulfur dioxide observations in the atmosphere. And sulfur dioxide is destroyed by photochemistry, so it doesn't have a long lifetime in the atmosphere. So in order to get variations, you need to be producing it in the planet. And the logical way of producing it is volcanoes. So we should be seeing this SO2 should be produced by volcanoes, and we should be seeing some kind of activity at the surface related to volcanoes. And so there have been infrared measurements. There is a small infrared window where you can actually see the surface, and some of the volcanic centers are hot in the IR. Whether or not the atmospheric correction has been done properly or not is a subject of debate in literature, but some of the volcanoes are a bit hot, so maybe that says they're active. There are some of the volcanic centers here. There's a geologic map of these. That's these points here. And again, that infrared window where you can see the surface, those are two observations here taken at different times using Venus Express. And what they see is different patterns at different times. The logical explanation is that some kind of eruption is going on in the second image to explain why the temperature has suddenly increased from the baseline. But again, we don't have very many observations of this, and there's always a debate about whether the atmospheric correction has been done correctly or not. So these infrared signals are somewhat ambiguous. There has been, this was a paper last year where they went back and looked at all the old Magellan data, and they basically georeferenced everything together. And I don't know who did this, but someone went through and flicked between all the images to see if they could see changes. And in this particular case, they found one place in the whole planet where if you look closely, you can see this thing here has changed shape, and this thing here wasn't here in this image, at least if you squint quite well. So you can see why the guy had quite a difficulty finding this. It's quite subtle, but it's quite convincing. If you look at the data yourself, you can see these changes. So maybe a new lava flow on Venus. So I think this is relatively, we should be expecting when we go back to Venus to actually find some changes on the surface. Maybe even more substantial than these hints that we've had from Magellan data. I'm sure you've heard as well of phosphine, and I couldn't come to a talk about astrobiology without talking about phosphine in the cloud decks of Venus. I'm not going to say anything about this. I have no opinion on this, but other people do. Phosphine, no evidence of phosphine. More phosphine again. This is a preprint. Look at the date here. That's this year. It's GRL. It's in review. Who knows what that's ever, if that's, it's having a hard time. It's been in review for 2 years. So I have no opinion on this. There's phosphine, possibly, maybe not. Who knows? But yeah, whether that means life or not is a different matter. So yeah, maybe there's some kind of exotic life in the atmosphere of Venus. Why not? Could be fun. But yeah, I'm a geomorphologist, so atmosphere is not really my thing. I'm pretty sure there's no life on the surface. So the future exploration of Venus, we have 2 American missions, Veritas and Da Vinci, and they're well on their way to getting there, being designed and built 2029, 2030. There may be a new Soviet mission as well. So Da Vinci is quite exciting. It's going to go down and actually go to the surface. So the first lander for decades. And Veritas is going to image the surface. And the Indian mission possibly as well. But also, European Space Agency is sending Envision. It's been approved. We're all very happy. We have people in the lab who are working on this and have been working on this for a long time. So a range of instruments that will explore everything from the interior out to the atmosphere. But what excites me is there's going to be a new radar. And so we'll get maybe do some change detection. So that'll be cool. And I just have a little video of the mission showing how it should look when it gets there. This is obviously an artist's impression because this has not been built yet. But this is the atmosphere of Venus as you see it in the visible. And the spacecraft does some gymnastics in order to point its solar panels in the right way and radar in the right direction. And this is the radar piercing those clouds and getting a lovely observation of the surface of Venus. And so, yeah, hopefully Envision will go and we'll get some great new data for Venus. So as I said, we're going to skip these two. And we're going to go to Mars. My sort of, not my favorite planet, because I quite like the Earth as well. We are here after all. But the planet I probably worked the most on and published the most on. And I'm going to pretend you don't know anything about Mars and give you a few facts. So Mars, as you saw in the previous slide, is a smaller planet than the Earth, has a lower density, so it has a lower gravity. On the present day, it has a colder, it's minus 50 Celsius on average surface temperature, which actually varies between minus 130-ish and 30 Celsius-ish. Very thin atmosphere at the present day, 6 to 10 millibars. The atmosphere is mostly carbon dioxide with a very, very small amount of water. That means the atmosphere actually has a cycle of sublimation and condensation of both carbon dioxide, so the carbon dioxide ice condenses onto the surface, we'll come back to this, and so does water. So you have both these ices that condense on the surface and sublimate into the atmosphere. They have similar seasons to on Earth, which is kind of handy when you're looking at seasonal processes on the surface of Mars, and we do see seasonal processes. There's been no plate tectonics, which is kind of cool from a geomorphological point of view, because it means landscapes from 3.5 billion years ago are still visible now, and we can study them. Because if there'd been plate tectonics, they would have been erased. There is a topographic dichotomy boundary which separates the planet in two, which means you have two surfaces of two different ages, which is also kind of cool if you want to study more recent processes of Mars, more ancient processes of Mars. And just so you know, 1 day on Mars is about 1 day on Earth. It's a little bit different, which is a bit annoying when you try to do missions. One Mars year is 2 Earth years, which is annoying when you want to make repeated observations because you have to wait 2 years to get back to the same season if you missed it this year. So, yeah, you have to be patient. There's been a lot of missions to Mars. I'm not even going to start to name them. Many different countries, ESA made this beautiful chart. It's probably already out of date. The little arrows refer to ones that have gone in orbit, flyby, ones that are on the surface, rovers and landers. And why have we been sending white? Because I just showed you Mercury and Venus, and there's been a handful, less than 10 missions to both, maybe, you know. And why are we bothering sending things out to Mars? It's a bit easier orbitally to send things out rather than in. That's one reason. But also we think that Mars has been more habitable. And I'm going to just go through some of the arguments, geomorphological arguments rather than geochemical arguments, because I'm a geomorphologist. But there are also geochemical arguments as to why we think that Mars was warm and wet at the beginning of its history, so 3.5. So here we have present day, back in time to 4 billion years, and we think that Mars was warm and wet, and now is cold and dry. And essentially, here you have the different eras on Mars, and hopefully will not forget to, I won't say, I'll try and use dates rather than names, because I know not everyone's familiar with them. But here you have basically different sorts of activity, magnetic field that Mars used to have in the beginning, large impacts at the surface early on in history, like many bodies in the solar system, volcanic activity, which was big at the beginning of Mars's history and has tailed off. But more relevant for habitability is these 3 panels here, where we have evidence of sustained water at the surface early in Mars's history that then declines with time. And I won't have time to talk about this middle bit, really. Valley networks I'm going to show you, and alluvial fans as well. And as I said, I'm not going to talk about the geochemistry, but there's a lot of geochemical arguments, clays and hydrous alteration, which we see at the beginning in the old terrains, but we don't see very much of in the new terrains. So what is the geomorphological evidence for ancient liquid water on Mars? So one of them is the valley networks. And this is a color image from the HiRISE camera. Here's the scale across here. The first thing maybe that springs out at you are the impact craters. But if you look between them, there's these networks of drainage systems which can only really be produced by runoff collecting at the surface and draining into the channels, and then draining into bigger channels, and then combining into bigger channels. And this is on 3.5 billion years ago terrain. You can see that there are impact craters that have happened after these have formed, so we can make an approximation of their age based on how many impact craters are on top of them. Here's an even nicer view where you can see the valleys reaching up to this drainage divide. And again, as I said, they're punctured by these newer impact craters that are on top, showing that they're actually ancient. And that's backed up by the global view. So this is the global view of Mars, South Pole, North Pole, thesis over here. And this is the dichotomy I was talking about earlier. So you have the northern plains here, which do not have these valley networks. It's younger terrains. And then the southern highlands, which are covered, not completely, but covered with these valley networks. And in yellow are the clays. So clays are thought to be produced by long-lived aqueous environments. And so they actually, the locations where we find clays correlate with the locations we find valley networks. And you'll notice that there's an absence of these valley networks on some of the recent volcanoes, not all of them. So, yeah, widely distributed over the ancient terrains of Mars, showing that this was probably a global process happening 3.5 billion years ago. What other evidence do we have of continued aqueous environments? So as we move on in time, so as we come to more recent times, we have evidence of more episodic activity of liquid water. This is in the form of what we call alluvial fans, which you find in Death Valley, for example, on Earth, which are caused by episodic runoff, carving channels and depositing inside basins such as craters. And this is not a global map. Notice it's 60 north to 60 south, but all the longitudes, the two impact basins of Hellas and Argyre here. And you can see that they're globally distributed over these older terrains. The other thing you'll notice on this chart, so red is the alluvial fans, is other type of fan deposits that people interpret as deltas. And deltas mean that you're going into a lake. So also evidence for lakes on Mars. And this is, rather than the deltas, just another map showing that you can actually go through all the impact craters on Mars and look for craters which have an inlet and an outlet channel. You can look for ones that have evidence of lake deposits inside them. And so that means you get dots even more all over the place. So we have these systems that are thought to be temporary lake systems, episodic possibly, not long-lived, at the end of Mars's kind of wet period. And this is what those. This is actually a spectacular example, Eberswalde crater on Mars. There aren't many as beautiful as this. We don't. Yeah, it's not every day you look at a Mars image and this pops out at you. This is the kind of poster boy image of a delta on Mars, and you can see that actually the channels in this delta are inverted. So here they're down in the Mississippi Delta on Earth. The channels go down, but here the channels go up. And this shows there's been a hell of a lot of erosion on these since they were formed. We're actually inverting the landforms in it because they've just been eroded away by probably wind. And this is more like what we see usually for these kind of delta systems, is these kind of valleys coming in, then a sort of lobe that has a shelf on it, and if you look very carefully you can see a series of layers on this one, which is quite nice. Again, the same here. This is more typical of what what we interpret as deltaic deposits on Mars. This is an oblique view, and here the delta front and the delta foot down here. So these are more typical, sometimes not as obvious to interpret. This could be an erosional surface that's not related to the initial formation, for example. And these are some examples of those alluvial fans, both on Mars. Here you have a fan, the crater wall up here. Again, this is more typical style. You have the fan down here, craters all over it. and the catchment up here. This is the context for the same image. This is a zoom. And this is an example from Death Valley on Earth. This is a debris flow, alluvial fan debris flow dominated. You can actually drive along this road and stop and have a look. The size is somewhat smaller than the size of the ones on Mars. Some fantastic, I talked about inverted landforms. You get some fantastic systems, Aeolis Dorsa on Mars, where you have it, what we interpret as inverted channel systems, which look crazily like the meanders we get in fluvial systems on Earth. And all these are signs of the fact that Mars had a lot of water running around on its surface. So this is why the rover Curiosity was sent to Gale Crater. This is Gale Crater here, Mount Sharp in the middle. It's because we thought from orbit there were lots of interesting deposits, muds, clays, and so actually went there, and there they are, the mudstones, the fluvial sandstones, showing that we actually had runoff and transport, and the conglomerates from this alluvial fan formation process. So these episodic wet events in the history of Gale Crater. So what we saw from orbit was proven true by the rover in situ, and here are some of those conglomerates. You can see the pebbles here. Perseverance, you might have heard of as well, again sent to another aqueous environment. Not the same one, but this time a delta. So this is Jezero crater, 45-kilometer diameter crater. The delta is not quite as pretty as the one I just showed you, but is quite convincing. And again, some very intriguing signatures from orbital spectral data, for example, clays and carbonates, as well as the crater floor having volcanic rocks. And again, what we saw from orbit was confirmed when we actually got there, and I'm just going to show you one example. These are deltaic forcep deposits here, shown in the SuperCam image, and this little outcrop that's over here. And here is the interpretation. So this is the zoom in on what we were looking at just before. You can see that the deposits do this, that if you follow the layers, trust me, they do this, and not like just this with a unconformity. And so this is very, very typical of a Gilbert delta stratigraphy. So pretty cool. And Nicolas Mangold's published on these results last year, I believe. And so again, in situ confirmation using classic sedimentology of what we saw from orbit. So it's reassuring. This probably means that the other things we think are deltas on Mars probably are deltas too. So just to give you a sort of like view, take the green away, but this is what we're imagining for Perseverance, a crater lake with a delta, and the water flow is coming in from the inflow channel. What we do have in Jezero is also an outlet, which we don't have in this particular example, but this is kind of like how we imagine that system being. So I hope then that's a very quick view of early Mars. So we were basically in this bit here. So the valley networks here, and then around here, the Jezero and Gale crater, alluvial fans and deltas. But what about this bit on the right-hand side? Where did, in fact, all this water go that we had on the surface? Where's it gone? There's a couple of answers, and one of those answers is that we have water ice polar caps and we have permafrost. But what people often don't realize is we actually have glaciers on Mars, and this is quite cool as a geomorphologist to see this. So this is a 3D view of a glacier on Mars. And you're going to say, well, I can't see any ice in this. That's totally normal because ice is not actually stable at the surface. So what ends up happening is that it sublimates away, and gradually as the debris comes to the surface, it forms a lag. And so actually the lag at the surface, so debris-covered glacier, this is a debris-covered glacier. And the lag at the surface protects it from further sublimation. So you end up basically armoring the surface with debris, and the glacier is preserved and it looks the same color as the rest of the surface, but you have these lobate forms extending from mesas, for example, here. And this is called this initially was called a lobate debris apron because there was it was spotted back in the Viking orbiter times. These are very large features. There'll be a scale bar on the next one. And so it can be seen in even low resolution images, and people kind of thought they were glaciers, and so here again, nearly 10 kilometers in length here. And it wasn't until we got radar data that penetrated these that the debate was finally closed about what forms these, because you can see through them. So this is the same, this one here is the same one that's shown here. You can actually see, so this is a simulation. So with satellite radar systems, you get reflection from the surface of the planet, and that can cause clutter. So this is a simulation of the radar just with the topography. So you simulate what the radar would do when it hit the topography, and you can see that there are look like underground reflectors in the simulation. So wherever you see underground reflectors in the simulation, if you see it in your actual data, it's not an underground reflector, it's just the topography creating artifacts. So what you'll notice is there's nothing here, for example, but there is something here. So that means that reflector we can see in the actual data is a real one. It's not clutter. And again here, there's no reflector actually in this gap, and etc., etc. So if you correct, so this is time of flight. So this is time in microseconds, so time that takes from sending the signal to coming back to the instrument aboard the spacecraft, and it doesn't give you actual depth. So in order to get the actual depth, you need to know the permittivity, so the speed that the radar goes through the material. And so if you use the permittivity of water, you actually recover a flat surface which represents the terrain underneath. And so by inference then, we have water ice. And so this has not much been done. This is just an example. This has been done on many of these lobate debris aprons. And basically these are debris-covered glaciers. And we have some we have lots of other debris-covered glaciers on Mars. I'll show you a map in a second. But we don't just have this radar evidence. We also have evidence of flow in terms of these lineations. There's things very similar to crevasses as well. And this is the interpretive map on here. You get some terminal features like moraines. And in rare cases, you also get deformed impact craters. Why you don't get more deformed impact craters is a different thing, but yeah. So these are complex systems which are like glaciers on Earth, but like glaciers on Earth in very cold places like Antarctica, like in very cold places like high altitudes in Chile, not like on Mont Blanc, where you actually have quite a lot of water. So these are actually deforming really, really slowly over really long time periods because they're what's called cold-based glaciers. There's no melt, and they're deforming under their own weight rather than sliding on the wet surface, which is most glaciers on Earth are sliding on the melt underneath them. So glaciers on Mars contain a lot of ice, but that ice is not melting. Well, maybe sometimes in certain cases, but if you want to talk about that, I could talk about that afterwards. There's a few pieces of evidence that say maybe glaciers on Mars have sometimes melted. Just to prove to you that I'm not talking about some choice little images in one or two places, this is Mars in its entirety, and these are the mapped areas with glaciers. So we have stupid names for them, so I won't go into why, but they're LDA, CCF, and LVF, so lineated valley fill, lobate debris apron, and concentric crater fill, which is not always concentric, so it's a silly name. But essentially, these are glaciers just in different topographic settings, and the names were invented before we knew they were glaciers, so it's just simpler to call them debris-covered glaciers. So the one thing you're going to notice straight away is they're confined, and not just because they didn't survey those areas, They didn't survey those areas because there's no point surveying them, because it's like 1 or 2 data points and it would just take forever. But they are constrained to this sort of 60 to 30 degree latitude zone. That suggests that there's some kind of climatic factor that's coming into play. And essentially, Mars has a wide variety of obliquities, so axial tilt, which can change the climate entirely. And so you can shift where the ice is stable depending on the the obliquity. So this is present day, more or less 25. These are water ice polar caps. You point them more towards the sun, they sublimate away, and the ice stability goes to lower latitudes. So this is where we think those glaciers are being deposited. And if you go even more extreme, you can actually even maybe deposit glaciers on top of the Martian volcanoes. So this is not a crazy number that I've just plucked out of nowhere. Mars can actually go up to really high obliquity, and this has been shown by orbital modeling into the past, and actually can go down to almost 0 as well. So has a really extreme effect on the climate, and we actually have ice ages essentially on Mars. We're currently in an interglacial, more or less. What's present day Mars like? I'm going to give you a quick overview of present day Mars. I thought I'd start by looking at aeolian processes. We've just been on June, so I thought you could do a bit of compare and contrast with what you've just seen, the Dune de Pilar. Tell me what you think is different. Then I'm going to talk about some fun stuff to do with sublimation, because there's some fun things that happen there. And then also just a couple of other things that are really neat, and we can do with the really high resolution data we have of Mars. So because we have 25 centimeter per pixel images of the surface of Mars from the high resolution science imaging experiment, or HiRISE. And HiRISE has been operating for over a decade, not 2 yet, but will be soon, hopefully. And that means that we've been able to take repeat images of the surface of Mars, years sometimes apart, sometimes less. And you can actually see, this is a sand dune. It's not very easy to see, admittedly, with this light, but this is the crest and the slip slope here, and this is the back of the dune. And essentially, you can see it moving this way with time as the dune migrates. So we can see dunes moving on Mars. This is not the only example. What you'll notice is it's not yellow, it's black. And this is because this sand is not quartz sand, it's basalt sand. So actually a different composition to what you get on Earth, due to the fact we mostly have basalts to erode on Mars. It's very convenient, nice bright background here. You can see it moving very nicely, but it's not the only case. We have centimeters to meters per year movement on dune fields on Mars at many places. So aeolian activity is super frequent. And we've been to visit one of these dunes, actually with, this is the Curiosity rover, and you can see a slip face of up close here, only a few meters high in this particular case, but classic. We didn't get to see these today, but these are classic slip face morphologies. Maybe you made some of these by stamping on the sand, these little flows, but this is a classic morphology for sand dunes. It's just black as opposed to yellow. So lots of aeolian activity on Mars, but not only deposition in forms of sand dunes, also these cool forms called yardangs. So that's erosion of friable rocks by the wind and sand, basically like sandpaper. This is an image from Mars here, and an equivalent image from Earth, where we actually have black sand. Yes. So it actually looks very similar, apart from there's a car in this one, and no car in this one. So we haven't got jeeps on Mars yet. We just need a rover just here, and that'll be perfect. Yeah. So yeah, yardangs, also aeolian erosion, but also aeolian erosion. The rover's seen this at the small scale, what's called ventifacts, where we actually have scouring of the rocks on the surface by wind. This is a view from the Atacama, which frankly looks exactly like the surface of Mars, apart from the sky is blue. Sometimes it's not very blue, sometimes it's kind of brown as well. And essentially you can't really tell the difference between these blocks of basalt in the Atacama and the blocks of basalt you find which have been eroded by the wind on Mars. Something I wanted to share with you as well is something I've kind of discovered as I've started studying the surface of Mars, which is sublimation can do things. So, as I explained, we have a seasonal carbon dioxide cycle on Mars. I'll just go over that again. So essentially the atmosphere is carbon dioxide, and it gets cold enough in the winter for that carbon dioxide to condense onto the surface. Well, I say condense, but we don't know if it's snow or direct condensation. There's evidence of both. But whatever puts it there, it ends up extending to 50 degrees latitude continuously. So you actually have, even on telescopic observations from Earth, you can actually, if you've got an extremely good telescope in a very clear atmosphere, you can actually watch the seasonal cap grow and shrink on Mars. It appears as a white blob on one end of the planet. It extends to 50 degrees continuously, but it'll extend up to about 30 degrees latitude discontinuously. So on pole-facing cold slopes, you'll actually get CO2 frost forming as well. And as that frost extends up to its maximum extent at winter solstice, and then as you warm up again, it will sublimate away. And so gradually you've been realizing this can do things. So this is the first thing, this is let's say the first sort of active process that really people started to publish about since about 2000-ish. And this is CO2 jets. So near the poles of Mars, this CO2 ice gets to meters in thickness, and CO2 ice has the peculiarity of being translucent. And so what can happen is early in spring, that light penetrates underneath the CO2 ice, warms up underneath. And so it's actually the ice underneath between the surface of Mars and the slab that warms up. And it gradually lifts that slab and breaks it. And so that is what you're seeing here. These random spots and fans on the surface is, in fact, the effect of when that pressure builds up, the ice cracks, and psh, out comes a jet and deposits the dust and sand that's underneath on top of the ice. So you have beautiful white ice. It breaks and forms this jet, and you get a deposit these weird black splotches on the surface. And these change with time. So this is what we're showing here. This is a zoom of this part here. Nothing, a thing, psh, a smaller thing, a small thing. These actually change with time. And this happens every year. Seasonally, you get these weird surface features. They look a bit like bushes in some cases. So some people have said there's growing algae on Mars and vegetation and things like that. It's all very fun. The conspiracy theorist people had a great fun with all this stuff. It's just seasonal CO2 processes. So this is, we think this might actually be doing some geomorphic work. So in some cases, we think these eruptions are actually happening in the same spot every time. And the gas is escaping using the same route. And so it's carving little channels into the substrate. And these have a great name. They're called spiders. And if you type spiders on Mars into Google, you'll get David Bowie. That's not what I'm searching for. They're araniiforms, if you want to call them the scientific name, but everyone calls them spiders. But you'll have to type spiders on Mars, like geomorphology or something, to get the right thing. You can see they're hundreds of meters in size. And they are, their arms, the jets actually occur at the thin bits of these networks. So the gas is actually coming this way out from the center. It's kind of strange. But we've never really seen them growing. So maybe they're not actually happening by this process. Who knows? So I don't think this is necessarily resolved, but I mean, it's the only thing we can think of that could make these weird network, dendritic networks, is this gas escape mechanism. And so this is kind of like the schematic view of what's going on. You have the CO2 frost, you have the surface of Mars, it transforms into a translucent slab, again, the surface of Mars. You have the basal sublimation that builds up gas pressure, cracks, and then you get these spots at the surface. And then if you keep repeating this year after year after year, it erodes the little channels in the surface, and then when the frost goes away in the summer, you see images like this, and you have these little holes carved in the surface and making these spiders on Mars. Yeah, so they're kind of, we probably call them trees on Mars, but actually that's probably just as misleading. So at least you wouldn't get David Bowie when you search for it, but well, whatever. They decide to call them spiders, whatever. These are only features that are found near the southern polar cap of Mars. Why only near the southern polar cap? Well, the ice deposits, the CO2 ice deposits, slightly thicker than in the north due to the current orbital configuration of Mars. But honestly, if they're ancient features and they take a while, because we haven't seen them changing, so they obviously take a long time to make. Why they're not near the north, who knows? Mystery. So I'm going to now talk about gullies on Mars. This is one of my favorite topics. I studied these since my PhD, and at the beginning, gullies on Mars, when they were first discovered in 2000, were interpreted as signs of surface liquid water on Mars, and so surface liquid water, but coming maybe from an aquifer, which is super exciting because if you have an aquifer on Mars, you could have life under the surface. Mars is suddenly a habitable planet. This was a science paper, obviously. And obviously it caused massive debate. Can't have we can't have aquifers on Mars, that's crazy, etc., etc. But it was the only way you could get liquid water at the surface at the present day because it's just not stable. Thermodynamically, you can't create liquid water from melting ice, and you know and you can't and you can't melt snow. There's no rain on Mars at the present day, so it's a bit of a problem. So the only way that the authors, the discovery paper of these gullies could find of making stable liquid water was to bring it up from the subsurface, with the very big conclusion that Mars had aquifers. However, loads of research has been done on these now, and I'm showing you an image here of actually these gullies actually form on sand dunes. It's super hard to pump up a sand dune to the top of a sand dune from an aquifer. Super hard to do. You find these all over the place on Mars at the tops of slopes where it's super hard to get aquifers coming out. So the aquifer hypothesis is very quickly discarded. But what you do notice on this map is a similar latitudinal distribution to those glaciers that I showed you before. They're only found in this 30 to 60, but they're concentrated in this 30 to 60 latitude in both hemispheres. In blue, there are pole-facing gullies, and in red are equator-facing ones. You'll notice that anything to around 40 degrees, they're only pole-facing, for example. The reason they're less frequent in the northern hemisphere is not to do with any particular climate condition. They need steep slopes to form, and there are more steep slopes in the south than in the north. So it's literally an availability of steep slopes for them to form on. There's no other bias in that data set. So they're found equally in the north as in the south. There's just fewer steep slopes in the north. And so this latitudinal, strongly controlled latitudinal distribution speaks to a climate factor. And so what people said was, well, maybe we have higher obliquity, we have snow at the surface, and there's some microenvironments, and we get some melting, and they form these gullies. And so that's all good. That could work, and that's something I talked about in my PhD. But then I finished my PhD in 2010. So that was between this image and this image. And so in my PhD, there'd been a few observations of some changes in gullies, but it wasn't really anything. It was just little blobs. It wasn't anything. Could just be mass wasting, a little bit of stuff falling down slope. But But then we started to notice, with repeat imaging, with the high resolution camera, that it wasn't just small things that could be dry mass wasting occurring in these gullies. You're actually getting significant changes with sediment transport. So here a new channel forms, and here it gets longer. And if you've got good eyes, you'll see the deposit here that's associated with that new channel, which wasn't here in this one. And here, this is a really nice little GIF. You see this is a giant rock that must be about 5 meters that's moving down this channel. Yeah, that's pretty significant. And so we're not just, and these are on slopes that are too low for just dry mass wasting to transport these things downhill. And same here, these are like 15-degree slopes where you can't just dry mass wasting, wouldn't be able to propagate onto these slopes. So there must be some kind of fluidization happening, and this is happening now at the present day. And liquid water really isn't possible at the present day. So we have to think of some other way of making these changes. Oh yeah, this is my favorite one. This is a really giant blob that comes all the way down. So this is just this is up and this is down. I turned it around so you have it as big as possible. Because if I put it the other way up, you couldn't see anything. So yeah, you see this filling up with sediment. You see this huge lobe forming here, and you see the sediment emptying from the upslope area. So these are, okay, they're not giant, like kilometer cubed of material, but they are, hundreds of meter cubed of material moving down these slopes. It's not small amounts, and they're moving out onto slopes that are too low to explain using just dry. If you just have a dry landslide, it couldn't do this. And the shapes of these forms are very similar to debris flows on Earth, and debris flows on Earth are fluidized by liquid water. The thing we noticed was that, so these black bars I'll explain, this is seasons across the bottom here. So what's called solar longitude, L's of S. And here, what I've done is I've translated that into words. So the different seasons across here. And so essentially, this in blue, this is the continuous ice I was talking about. So when you have the ice, CO2 ice over the whole surface. And with the dotted line, this is where you get discontinuous deposits. So not continuous ice deposits, but discontinuous deposits. And the black lines are observations of changes in gullies. So in the first image, you don't see the change, and the second image you see the change. So the change happens somewhere in the black bar. We don't know where in the black bar, but it's happened somewhere in the black bar. And so what you see is that all of these changes are occurring when frost, CO2 frost, is present on the surface. Maybe this one, not quite, but without exception. So when CO2 is on the surface, the temperatures are minus 130 Celsius, so way, way, way too cold for liquid water to be doing anything at all. But it's happening here when that CO2 ice is in the middle of sublimating. So we thought, well, it must be, maybe it's something like the spiders that we saw with these jets, maybe it's doing something. And so we think what's happening is the CO2 ice is actually sublimating away and causing these movements, and it's not liquid water. So we have to be really careful when we're interpreting landforms on Mars and on other bodies. If we see something that looks like Earth, that looks like liquid water, maybe it's not. Maybe we're being tricked by, the different planetary conditions. And we're still investigating how this CO2 sublimation, both in the laboratory and modeling, how the CO2 sublimation actually leads to transport of such large things and channels and such like. Why does it look like wet debris flows on Earth? Other things, exciting, cool things that slope processes are happening on Mars. These polar avalanches. So these are on the north polar cap. We have these extremely steep, almost 80, 90 degree cliffs. And we actually get seasonal avalanches falling off them. We get also rockfalls occurring on Mars. You can see the little bounce marks where the rock comes down and the boulder comes to a standstill. And we actually did a little bit of a study on these, and basically we found that they were asymmetrical. So this is from 15 degrees south to 50 degrees south. This one's from 15 degrees north to 40 degrees north. So, and this one's between 15 degrees north and south. And what you'll notice is a very strong north-south asymmetry, north-south preference. And then in the different hemispheres, there are more rockfalls facing equatorwards, so facing towards the equators. And what we found was these are the slopes that experience the highest thermal stresses. So if you do a model of the thermal stresses experienced in a crater, then that over these are the slopes. So in the equator area, it's both sides, north and south, but not east and west. And then in each of the hemispheres, it's different. And these are the coldest temperatures and the hottest temperatures. And the reason it's symmetric, because it shouldn't be symmetric at the present day, is because we're looking at these tracks, and these tracks actually persist on the surface for hundreds of thousands of years. And that's enough time for Mars to have gone to actually cycle through. So perihelion, so the closest part to the sun of the eccentric orbit, varies in time. And so each hemisphere experiences more thermal stress than the other one. And actually, the rockfalls last about the same time as this cycle. And so that's why it's symmetric, is because actually it's enough time for us to have been with perihelion in the different hemispheres, basically. So we're sort of integrating over hundreds of thousands of years. And so this is why it's symmetrical. We also get these cool things called slope streaks, which are only found on Mars. And we think these are dust avalanches. But I was at LPSC last week, so Lunar and Planetary Science Congress in Houston, and we're still talking about whether these are liquid water or not. So I don't study these, I don't know. But yeah, so these are fun, they're cool. We don't know we don't know how they're formed. We haven't found them on other planets yet. Maybe just we need to wait and have better images. But they're kind of fun. Also, you can see they can have really exciting shapes. But we also get things that look very much like find on Earth, landslides. I had a student that studied these. These are not anything magic, they just happen like they do on Earth, but it's kind of neat because on Mars we get way more of these to study because, as I said, we don't have plate tectonics to erase them. We don't have all this pesky vegetation and erosion to take them away. So we can actually study way more landslides on Mars than we can on Earth. So this is one way in which Mars can probably tell us about how things are happening on Earth. And one thing we don't get also on Earth is a lot of fresh impacts to study. So actually Mars allows us with these repeat images to correct the impact of flux for Mars and for other bodies in the solar system using these new impacts. And these new impacts are cool as well because they reveal at the surface what's in the subsurface. And so we sometimes get them into icy deposits, so we actually are able to probe the permafrost of Mars using these deposits. I didn't put one of those in here because I didn't think I would have time to talk about it. What's next for Mars? The very certain next thing for Mars is that there's going to be the Mars Moons Explorer. So this is Phobos, one of the 2 moons of Mars, and that's actually going to be the next thing for Mars. So not actually Mars, but the next thing around Mars. There's Mars sample return, of course, because the samples have been collected on Mars. We're going to have some sample return. We've no idea when, how. Probably the Chinese are going to get there first. So there's probably a Chinese mission in here between these two. There's the Mars Ice Mapper, which would be really awesome because it would actually find out more about those glaciers, but it's got a question mark on it because no one's built anything yet. And NASA is in, it's out, it's in, it's out, so who knows. So I think Mars is going to be kind of quiet in the next decade. We're probably going to get way more exciting stuff from Mercury and Venus, so it's a good job I work on everything, because otherwise I'd start running out of things to do on Mars. And I just briefly, very quickly in the last 5 minutes, I just want to talk about this intriguing dwarf planet Ceres, which is a little further than Mars, I'm in agreement, but is an intriguing body, especially geomorphologically, and intriguing possibly in terms of habitability as well. So Ceres is an icy dwarf planet. So it's not a rocky moon, it's not an icy moon, it's kind of somewhere between the two. And Dawn visited Vesta, then Ceres, and the surface is way more complicated than we anticipated. Hydrated mineralogy from the spectral data, and evidence of cryovolcanic activity. Hoona Mons here, which is the famous cryovolcanic dome on the surface of Ceres. So some really fascinating geomorphology, some beautiful images of the surface. And one of the big questions still is, what is the extent and amount of water ice in the crust? So we have some evidence from the gamma ray and neutron spectrometer that, so this is water equivalent hydrogen. So this is basically the number of 29% ice basically is the blue dark colors near the poles, and then 16% ice is the red colors, and that only penetrates the top meter. So this is ice in the top meter of the crust basically, more or less. We also have evidence of landslides, which are more or less fluidized, which are thought to indicate, ice in the crust as well. And so maybe up to 40%. And so we've actually been, with a student of mine, been looking in a bit more detail at some of the craters on Ceres. Specifically, what we've been doing is looking at this, which looks totally normal, maybe. So you guys, these are talus slopes with outcrops at the top of the slope here. And he went along and actually mapped these over the surface of Ceres. And it was actually, to me, it was relatively surprising to find such nice outcrop and talus deposits, because on the moon, we don't have this at all. The moon is also an airless body that undergoes an equivalent amount of space weathering and impact cratering. So to me, it was quite surprising we had these outcrops at all. And he actually went along and mapped these everywhere. And they have a hemispheric pattern. So in the northern hemisphere, they face south. In the southern hemisphere, they face north. And so they're on the coldest slopes, poleward slopes. And so this is represented here in these two examples. This is from the global data set. And these two are just these two craters just in the north and south. And you can really see how these outcrops are really biased by where they are. And so this shows actually that we probably have a different form of crater degradation to what we're expecting, where you actually have an ice-rich crust exposed to the atmosphere that sublimates and degrades, forming these talus slopes. And the initial degradation of the craters is by wall retreat over time. And so the poleward-facing slopes retreat slower than the equatorward ones. And in the end, the process slows down. These outcrops are less exposed. They become smaller and smaller with time. And the sort of, let's say, standard crater degradation that we see on the moon takes over, where you have impact gardening and diffusive rounding of the terrain. So Ceres was this was a big surprise. This is new work that we're submitting for publication very soon. And so even the asteroid belt can have surprises when you look at things really closely. And so, as I said, Dawn went there. We have the best images of 3 meters per pixel. And so every time you get high resolution imaging, you get surprises. And I think that's going to be my last slide. So essentially, my conclusions from all of this stuff that I've been talking about are that we have rocky bodies that are remarkably different and diverse, considering their proximity in the solar system. The habitable environments are rare, Earth and perhaps Mars. Venus, if you believe phosphine in the atmosphere. Ceres, cryovolcanic, so we may have, some water actually underneath the surface. And I hope I've convinced you that looking at these bodies with detailed images really helps us to understand what's going on at the surface, its climate and different processes that are going on, giving an insight into both habitability but also the environments on those bodies. So thank you very much for your attention, and I'll take your questions.